Consider this. You want to make a delicious sandwich. You have a set of steps you follow, right? First, you get 2 slices of bread. Then you spread some butter. After that, you add your favorite fillings like cheese or ham. Finally, you put the 2 slices together. That set of instructions, that recipe, is an algorithm. It's a step-by-step guide for getting something done. Computers use algorithms for everything they do, from playing your favorite song to sending a message to a friend. It's the science of making things happen in the right order. Now let's think about how a computer might follow a recipe. It doesn't have hands to make a sandwich, but it has a processor to follow instructions. An algorithm for a computer is written in a language it understands, like Java. These instructions tell the computer exactly what to do with information or data. Whether it's sorting a list of names, finding the fastest route on a map, or even figuring out the best move in a game of chess, an algorithm is the brain behind the operation. It's all about creating a clear, logical path from a problem to a solution. Imagine you gave your sandwich recipe to a friend. If the steps are clear, they'll make a great sandwich. But what if a step was missing? What if you just wrote, "make sandwich"? Your friend would be confused. Computers are the same. They need very precise, unambiguous instructions. An algorithm must be foolproof, guiding the computer through every single possibility without getting stuck. This precision is what makes computer science so powerful and so fascinating. It's the art of creating perfect, repeatable recipes for solving problems. So an algorithm isn't some scary, complicated thing. It's just a set of rules. You use them every day without even thinking about it, like when you tie your shoelaces or follow directions to a new place. When we write algorithms for computers, we are simply translating our human way of solving problems into a language the machine can execute. And by doing that, we can solve problems that are way too big or too fast for a human brain to handle. Science! Let's say you have a huge pile of socks and you're looking for your favorite pair of blue ones. How would you find them? You'd probably pick up one sock, check its color, and if it's not blue, you'd put it aside and pick up the next one. You'd repeat this until you find the blue pair. That's exactly how a simple searching algorithm works. It's called a sequential search. The computer goes through a list of items one by one from the beginning to the end until it finds what it's looking for. It's a very straightforward method. This one-by-one sock-finding method is great if your sock pile is small or if your blue socks happen to be right on top. The computer finds it quickly. But what if you have 1,000 socks and the blue pair is at the very bottom? Well, that would take a long time, wouldn't it? The same is true for the computer. A sequential search is fast for small lists, but becomes very slow for massive lists, because it might have to check every single item to find the one it needs. It's all about the size of the problem. Now, let's try another problem, finding the biggest number in a list. Imagine you have a list of your friends' heights, and you want to find the tallest person. You'd start with the first person and say, "Okay, you're the tallest so far." Then you'd move to the next person. Is this person taller than the one you thought was the tallest? If yes, they are the new tallest so far. You keep doing this, comparing each person to your current champion until you've gone through the whole list. The last person you marked as tallest so far is the winner. This method of finding the biggest number is pretty efficient. Think about it. You only have to go through the list once. It doesn't matter if the biggest number is at the beginning, middle, or end of the list. You still have to check everyone to be sure. So, whether the list has 10 numbers or 1,000,000 numbers, the computer just has to make one single pass through it. Its speed is directly related to the length of the list, which makes it a very predictable and reliable algorithm for this kind of task. Here's a cool puzzle. Imagine you have a bag of marbles and you want to know if every single marble has a different color. Are all the items in your collection unique? How would you figure this out? A simple way is to pick out the first marble, then compare it to every other marble in the bag. If you find a match, you can stop right away and say, "Nope, not all unique." If you don't find a match, you pick the second marble and compare it to all the remaining ones. You keep doing this until you've checked every possible pair. This method works for sure, but think about how much work it is. If you only have a few marbles, it's fast. But what if you have 1,000 marbles? You'd have to make nearly 500,000 comparisons. That's a lot. For a computer, this algorithm gets slow very, very quickly as the list gets bigger. Finding a duplicate early on makes it fast, but proving that duplicates exist takes a huge amount of time for a large list. It's a classic example of how a simple idea can become computationally expensive. Now for something that looks complicated but is just another recipe multiplying matrices. Whoa, that sounds advanced, but let's break it down. A matrix is just a grid of numbers like a spreadsheet or a bingo card. To multiply two matrices, you just follow a specific pattern of multiplying and adding. Think of it like this. To get the number for one spot in the new grid, you take a row from the first grid and a column from the second grid. You multiply their matching numbers together and then add up all the results. You just repeat that recipe for every spot in the new grid. This process is very methodical. The computer just chugs along, multiplying and adding, filling in the new grid step by step. When is it fast or slow? Well, it depends on the size of the grids. If you're multiplying two small bingo cards, it's super quick. But if you're multiplying two massive grids with thousands of rows and columns, the number of calculations explodes. The computer has to do a huge number of multiplications and additions, so while the process is simple, it can be very slow for large matrices, which appear often in things like computer graphics and scientific simulations. There are so many other cool algorithms out there. For instance, have you ever wondered how a computer counts the digits in a number like 5,280? It uses a simple algorithm. Just keep dividing the number by 10 and count how many times you can do it until you get to 0. Or what about a factorial, where you multiply a number by every whole number smaller than it? That's another straightforward algorithm. There's even an algorithm to convert our everyday numbers into binary, the language of ones and zeros that computers speak. Each is just a clever recipe for solving a specific number puzzle. The wonderful thing about these recipes is that anyone can learn to write them. You don't need to be a genius with a lab coat, though lab coats are cool. All you need is a curious mind and a willingness to experiment. Start with a simple problem. How would you instruct a computer to sort a list of numbers from smallest to largest? Try writing down the steps in plain English first. Think about the edge cases. What if the list is empty? What if it has duplicate numbers? This is the heart of computational thinking. The journey into algorithms is a journey into problem solving. It teaches you to break down big, complex challenges into smaller, manageable pieces. It encourages you to think logically, to be precise, and to consider all possibilities. You can start today. There are many free websites and programs that let you experiment with code in a fun, visual way. You can build your own simple algorithm and watch the computer bring your instructions to life. It's an incredible feeling to see your own logic in action. So don't be intimidated by terms like algorithm or coding. At its core, it's all about creating instructions to make cool things happen. From finding a sock to creating stunning three-dimensional worlds in a video game, algorithms are the fundamental building blocks. They are powerful tools for creativity and discovery, and the best part is anyone can learn to use them. So go on, give it a try. You might just discover that you have the mind of a computer scientist.